All right, so here we are. We have a question that is talking about the half-life of iodine-132, and we're given the half-life, and we want to know what percentage remains after 24 hours. Okay? Now, do you have any ideas how would we would approach this?
Well, can we use the equation that we had that relates the concentration of A naught to A at any given time for first order reaction?
Very good. Do you remember what that equation is?
I have it in my notes, I think. Let's see, was it the A naught, or A equals A naught minus KT?
Oh, this one here, A at time t equals A naught minus KT.
Yeah, is that one?
No, this is for a zero order reaction, right? That's when the plot is linear. That's when you can say that your y equals mx plus b, right?
Oh, okay, yeah. So the first order is the other one?
That's right. The first order is, do you remember?
On my notes, I guess. Okay, so natural log of concentration initial over concentration at time t equals KT.
Very good. Excellent. And we also had this special relationship where the concentration initial over the concentration at time t, where t is your half-life, would always equal natural log of 2. And therefore, the natural log of 2 is equal to k times the half-life. All right? And this can allow us to identify k if we have the half-life, or identify the half-life if we have k. And for this type of question, both of those equations are going to be important. All right? Okay. Not the zero order, but both of these ones. Because in this case right here, if we try to propagate all of our variables, we have 4 variables in this equation here. We have the half-life is 2.295, right? But then we have 24 hours. We want to know what percentage is left over. So if we put in here for this one, 24 hours, now our half-life is in hours, so we can just use that and keep this to 24 hours. 24 hours times our k, we don't know our k, and we were wondering what percentage will remain. So we could say that that's our variable, because if this is 100 over some percentage, then, or 100 over however much you have left, then that will equal a value, a ratio, a fraction of what we have left if we say this is 100. Actually, sorry, this should be 100 over x, where we can find out what percentage we have left. There we go. But we're left with 2 variables still. So what can we do?
I guess you said we could use that other equation, but I'm not sure how.
Well, see, what this has is just 2 variables, and we know one of them, don't we? We know the half-life is 2.295.
Oh, okay, yeah. So we can get k.
That's right. So here we're going to have the natural log of 2 divided by 2.295, which is our half-life, and that is going to equal our k. All right, so natural log of 2 divided by 2.295, 0.302. So k equals 0.302. We can then plug that in for this k over here, multiply that by 24, and now we have the natural log of 100 over x being equal to 7.24. So let's rewrite this now. Natural log of 100 over x equals 7.24859. 8. I forgot to round up. I kept writing the numbers. It wasn't rounding up. All right. Now, how do we solve that math? Do you remember?
Oh, natural logs? Well, I guess I don't remember.
All right. So when we have and I'll bring over a little scratch piece of paper to write this bit on. If we have the log of x over y, then that can be rewritten as the log of x minus the log of y. Do you remember that?
Not really, but now I got it.
Okay, so natural log is just log base e of 100, or x, log base e instead of log base 10. So I can rewrite this as the natural log of 100 minus the natural log of x equals 7.25. Okay? Now I can take the natural log of 100 and I can take 7.25 and then subtract that. All right, 2.64 equals, and I'll divide that by -1. Get that -1 over there. So the natural log of x equals -2.64. And then I'm going to raise e to both sides, or take e and raise it to both of these values. E to the natural log is e to the natural log. See, e to the natural log of x will equal x. There we go. And e to the -2.64 equals 0.071. All right, so that is my percentage that remains, right? Because it's 100 over 0.7. So that's my percentage that remains after 24 hours. Okay, good job. So we learned how to use, reminded ourselves how to do some math with natural logs, which is important. All right, what's the half-life of this new element if after 2.5 hours only 1.3% remains?
Okay, so let's see.
Before you do that, let's let everybody at home push pause and try to solve this problem. Okay, this is your exercise. You have to do your exercises. Okay, after you've done your exercises and tried your best here, now we're going to walk ourselves through it.
Okay, so yeah, you use that integrated rate law equation, natural log of the concentration of A at initial over the concentration of time equals KT.
Okay, very good. And what do we do here?
1.3% remains, so you could write 100 over 1.3.
All right, good. Natural log of 100 over 1.3. That's how much remains.
We want to know the half-life, though. That's after 2.2 hours, so you can say equals K times 2.2 hours.
Okay, very good. So 2.2 hours. This is in hours now, but that's all right. Our half-life is going to be solved in hours. Now, we don't know K for the reaction.
No, but we know that the natural log of 2 equals KT, so T1/2, that is, yeah.
Very good.
So if I take the natural log of 2 and divide it by my, what do I have here? Oh, I don't have my K yet, but I have to solve that equation there for K.
Very good. Natural log of this ratio here divided by 2.2 will equal our K. So let's do that then. 100 divided by 1.3, natural log of that value, right, divided by 2.2. 1.97 is our K. And so if I throw in 1.97 here for K, then I can just say the natural log of 2 divided by 1.97. 0.351 is our K. Okay, we did it. Very good. Answer B.
Okay.
That's a good place to stop. See you next time.
Okay.